Welcome to This Explainer. Today we're strapping in and treating production-grade large language model systems exactly like what they really are, a high-stakes disaster survival scenario. Because if you've been building AI applications, you already know that crafting a clever prompt or a smooth router, well, that's really only half the battle. The true test is keeping your system alive when the underlying infrastructure inevitably decides to pull the rug right out from under you. So we are going to architect absolute resilience step by step right now.
Think about the number 55 for a second. That is the average number of minutes of weekly downtime across major LLM providers right now based on real production observability data. Now, the industry absolutely loves to boast about an average uptime of 99.46%. And honestly, that sounds fantastic on paper, doesn't it? But in the real world, that percentage translates to almost an hour every single week where your application could be completely dead in the water if you aren't prepared.
And that brings us to a pretty harsh reality. A system that depends on a single provider will go down multiple times per year with absolutely zero warning. The stakes are just inevitable. To put this into perspective, Anthropic alone tracked 114 incidents in just a single 90-day window, and the median resolution time was over an hour. Or take OpenAI, whose average uptime translates to roughly 16 hours of full downtime annually. These aren't freaks of nature, you guys. These are just the standard operating conditions of our industry. So if your product is losing customers during every provider outage, it's really not the provider's fault anymore. It's an engineering problem.
Okay, let's dive into the specifics here. We're calling these the 5 faces of failure.
Before we can actually build our survival tools, we have to understand the specific monsters we're engineering our systems to survive, right? Generic network error handling just won't save you here. There are 5 very specific ways providers are going to fail you. First up, transient errors. These are your standard, everyday network glitches. Second, rate limits. That's when you're simply calling the API too fast and you hit your quota. Third, sustained provider outages, the big, scary, multi-hour blackouts. Fourth, and honestly this is a sneaky one, soft failures. This is where the API actually responds, but it refuses the request or it breaks your schema. For instance, Claude's 529 overloaded error, which is a classic soft failure, climbed to a staggering 11.7% of requests by late 2025. And finally, strategic failures, things like overnight price hikes or sudden model deprecations. Now, a completely crucial part of our architecture is classifying all these errors into 2 distinct buckets, recoverable errors and non-recoverable errors. We only want to trigger our heavy-duty survival tools for recoverable things, like rate limits or server errors. If a request is failing because of a malformed prompt, which is a non-recoverable error, retrying it on 5 different models is just going to waste your time and your money. Strategic failures, likewise, demand a permanent architectural migration, not a quick temporary failover.
So let's build your primary survival tool, the fallback chain.
This brings us to our main line of defense. Now, a fallback chain is not just a try-catch loop that blindly hammers the same dead server over and over. It's an ordered, deliberate sequence of alternative LLMs that get triggered by failure. Let's look at a really concrete blueprint for a nuanced customer writing route. Step 1 is our primary. We go to Anthropic's Claude directly. But if that goes down, step 2 is OpenAI, a completely different provider. If OpenAI fails, step 3 is Anthropic again, but this time accessed via AWS Bedrock, which is a totally different infrastructure path. Finally, step 4 is Claude Haiku, a cheaper, faster, but lower-tier model. The absolutely crucial point here is that true resilience doesn't come from persistence, it comes from diversity. We're actively crossing diverse providers, access paths, and model tiers, just to ensure the message always gets through. Now, what's really interesting about this strategy is that every single fallback step is a deliberate trade-off across 4 axes: capability, cost, latency, and access mode. When you fall back to OpenAI, for instance, you might be temporarily accepting a 3x cost increase. And yeah, that sounds bad, until you realize that accepting a temporary 3x cost is infinitely better than your entire product being offline for 6 hours. Every single step on this matrix is a highly conscious business and engineering decision. All right, moving on to the next massive danger, let's talk about stopping the storm using circuit breakers. Here is where things get incredibly dangerous in production. A naive fallback chain can actually make a bad outage much, much worse by causing what's called a retry storm. Imagine you've got 500 requests per second hitting your system, and your primary provider is dead. If you don't have a circuit breaker, you are basically throwing thousands of requests at a failing server, forcing every single one of them to sit through a massive timeout before they finally move to the fallback. It's a nightmare. A circuit breaker, on the other hand,
actively monitors the health of the provider. Normally, it sits in a closed state, but if it sees a burst of failures, it trips to open, instantly bypassing that dead primary provider and routing straight to safety. And it'll occasionally let one request slip through in a half-open state just to test if the provider has recovered yet.
And this brilliantly illustrates the dramatic contrast. Think about a naive retry loop, 500 requests timing out for 30 seconds each. That equals 15,000 seconds of completely wasted wall clock time. Your users are just sitting there staring at a loading spinner forever. But with a circuit breaker, the first few requests fail, the breaker trips, and the remaining 485 requests fail fast and get routed to the fallback in under 10 milliseconds. Your mean time to detection drops from like 30 minutes down to 2 minutes. It is literally night and day for the user experience. But we have to ask the scary question. When all else fails, what do we do? That brings us to graceful degradation. Let's be honest with ourselves, a fallback chain is finite. Eventually, it ends. When your primary, secondary, tertiary, and your absolute last resort models are all down, throwing a silent exception and letting the app crash is never the answer for a production architecture. You really need one of 4 specific graceful degradation strategies, depending on your workload. If you're running a chatbot, giving a pre-canned response that acknowledges the high load is totally perfect. For background tasks, queue for retry so the work isn't lost. For informational queries, you might serve a slightly stale cached approximation. But what if it's a regulated financial decision? In that case, you absolutely want a hard fail with immediate on-call alerts, because in that specific context, a wrong answer is vastly worse than no answer at all. Let's move to the ultimate test and see how this all builds into what we call the boss fight, a 6-hour Anthropic outage. It is time for a chaos engineering tabletop exercise. We're going to simulate a major, multi-hour infrastructure blackout to prove that these concepts actually work when you're under heavy fire. Walk with me chronologically through this scenario. It's Tuesday at 2 p.m. At T0, Anthropic goes down. Bam. Immediately, the 503 errors spike, but our circuit breaker automatically trips, instantly shifting traffic over to OpenAI. The users feel a tiny latency bump, but no errors. Beautiful. At T plus 2 minutes, automated cost alerts fire off because, well, we just shifted to a 3-by more expensive provider. By the 1-hour mark, finance is totally aware of the sustained elevated cost, but engineering confirms the system is holding strong. At T plus 6 hours, Anthropic finally recovers. The circuit breaker detects it, closes, and traffic smoothly shifts back. And then at 24 hours, we do our post-incident review. Folks, this is what the system held actually looks like operationally. No dropped requests, just a known elevated financial cost to survive the storm. Which really leaves us with this ultimate truth. A fallback chain that you've just written on a whiteboard or maybe coded up but never actually tested in production is just a hope. It is not a system. Discovering that your secondary API key is invalid during a massive 6-hour outage is a catastrophic failure of discipline. So I want to leave you with this challenge. Are you relying on hope when the internet breaks? Or are you relying on rigorous, tested AI engineering? Get out there, break your systems on purpose, and build them to survive. Thanks for joining this explainer.